Okay, and let's see, why does that look different? Okay, let's see, what do you have in this quiz? We worked on a couple of these. Who's got a question on this quiz? Yes?
4.
4, let's look at 4. If we need to review anyway, I'd like to review with the quiz questions. Now, hey, on these quiz questions, I'm kind of expecting a little bit better grades on these, because you can correspond, talk with your lab partner, pull this quiz out. It's a learning tool. So I thought the quiz scores would be higher, and we can do some here. I don't have any problem with that. So, but you can correspond. Ooh, 4. All right, here we go. Here is 4. So nitrogen reacts with hydrogen to form ammonia. Well, let me zoom in on this. And then notice that this is the starting for this reaction, right? Then ammonia reacts with oxygen to produce nitrogen monoxide and water. So I'm going to turn the page here. Let's see what we got. Whoa, and then nitrogen monoxide turns into nitrogen dioxide. How many moles of nitrogen, okay, would we have to start with to make 10 moles of nitrogen dioxide? That's a great question. We are going to make 10 moles right here. That's our goal. Well, we need to figure out moles of nitrogen monoxide here, because that's produced in the previous reaction. I wish this came out on one page. Well, let's go this way. What is my mole ratio fraction going this way? 2:2, right? So we need to start with 10 moles of nitrogen monoxide here to produce 10 moles of nitrogen dioxide, correct? And where does this 10 moles of nitrogen monoxide have to come from? The previous reaction. This right here is the 10 moles. We are trying to figure out, I'm sorry, I should have pointed out, this is our final answer we're looking for right here. We're looking for the moles of nitrogen right there. So we need to start with ammonia here that's produced here. So let's go this way. And my mole factor fraction is 4:4, right? So that means in order to get 10 moles of nitrogen monoxide here, I would have needed to react 10 moles of ammonia, NH3. Where is the ammonia coming from? Right here. Is the 10 moles produced here for this reaction is the starting moles here. So finally, my last step, moles here. For nitrogen, my mole factor fraction is, my mole factor fraction is 1/2, right? 1/2. 5 moles. So I'd have to start with 5 moles of nitrogen, and then at the end, I would end up with 10 moles of nitrogen dioxide. Okay, what else we got for questions on this quiz? Yes, sir.
12, I believe.
12, let's see. And 12, I think, was the highest we could have got to. Let's see if 12 is one that we could do that. No, we haven't looked at 12 yet.
Okay. Go ahead.
12 we'll talk about right here. Yes.
11.
11. Okay, so 11 is a limiting problem. This would be a good review, because we'll do 11 and then we'll start where we left off today. So for 11, this is exactly what we worked at. Oh, I'm sorry. We have not done percent yield yet. This is a percent yield problem. We can start this out though. Let's start this out. So we won't get the final answer, but we're going to be close. Okay, so we have nitrogen plus 3 hydrogens. And we are making 2 ammonias. Ooh, I got a typo on here. Obviously, that should be a subscript, right? Okay, so we start with 50 grams of nitrogen. And this right here, we're going to talk about this today. This is your actual or experimental yield. This is actually what you got. We need to calculate our grams right here. Our theoretical. What should we have gotten? We need to calculate this. Now, again, when you do this in lab, you're going to lose stuff, right? And just go awry. You don't get the perfect amount of grams that you're looking for. So we need to calculate, this is going to be back to the original problems we've done then. How many grams of NH3 should we get if everything goes perfect?
50.
Well, let's do the math. How many moles is this? So we're going to take 50 grams of N2. One mole of N2, how many grams? One mole of N2, how many grams? Grab your calculator, grab your periodic table. The blood flows better to the brain when you're looking at a calculator and manipulating the calculator keys and looking at a periodic table. How many grams of nitrogen, 1 mole of nitrogen? 14.01 times 2 because it's N2, so we get 28.02. So 50, grab your calculator. 50 divided by 28.02. That's not right. We're starting with 1.784 moles. How many moles of NH3 should we produce? What is my mole ratio fraction here? How many moles should I produce? Yeah, 2/1. As soon as you point the arrow, that number goes on top. The start of the arrow where you started with goes on the bottom. So 2/1. Multiply this by 2. We should produce 3.5. I'll keep an extra 69 moles of NH3. Well, how many grams is that? One mole of NH3. How many grams of NH3? So 1 nitrogen and 3 hydrogens. (17.04). So theoretically, we should have gotten 60.8 grams. That's what we should have gotten. We only got 50. So we can do a percent yield, and I'll show you how to do that today, but you probably know how to get the percent yield knowledge. Look at this. Okay. So we'll come back and finish this baby. Let's look at where we left off. Last time, it was all about limiting problems, and that's what we're going to start off. For our limiting problems, you are given an amount of both reactants. Now, the problem we just did on the quiz is it didn't bother to mention hydrogen. So you're assuming that you have enough, where typically they say there is excess hydrogen. If you're only given grams of one reactant, we don't worry about the other one running out. We don't have a limiting problem. But if you're given grams of both reactants, you have a limiting problem. What do you got to calculate? How many moles of one that you have, how many moles of the other one you need, and then how many moles you have. So we already know this mole fraction right here is going to be 3 or 2, right? All right, so letter A, how many moles of aluminum bromide do you have? So this box right here is letter A. And then this box right here is letter B. And this box right here is letter C. And in this problem, we're going to calculate everything out here. So how many moles of aluminum bromide do you have? We have 53.34 grams. And then 1 mole of aluminum bromide. How many grams of aluminum bromide? Periodic table. Periodic table calculator. Periodic table calculator. Periodic table calculator. What is the molar mass of aluminum bromide? Molar mass for aluminum bromide. One aluminum, 3 bromides, that's a pretty big number. Always to 2 decimal places. Who's got it? Yell it out, somebody. 266.68. Yes? Yes, all right, vertical nods. I like to see vertical nods. Yes, so that gets us starting moles of, wouldn't you know, 0.2000. So we are starting here at 0.2000. How many moles of fluorine do we need? How many moles of fluorine do we need? 0.2 times 3 is 0.6 divided by 2 is 0.3, right? Now, what did we just calculate? What does this 0.3 mean? This means if we want to use up all of the 53.34 grams of aluminum bromide, we need 0.3 moles of fluorine. We don't know how many grams that is yet, but if we have 0.2 moles of aluminum bromide, which is 53.34 grams, and we have 0.3 moles of fluorine, then there is nothing left over. Everything's used up. So next logical case is, how many moles do we have? And the only way to calculate moles is to take our 19 grams and our 19.00 grams of fluorine F2. And 1 mole of fluorine, how many grams? How many grams? How much?
18.99.
Okay, 18.99, double that. 1938, that's around to 38.00 or not? 38.00?
Yes.
38.00. Ooh, so that makes my numbers nice. So that is 0.5000 if I kept my 4 sig figs, which I should. Moles of fluorine. So 0.5000 moles of fluorine. We'll go up here. This is 0.5000. Now, do you have enough fluorine?
Yes.
Yes, right? We have 0.5. We only need 0.3. That means if we have more than what we need, this is in excess. This one over here is limiting. We know that all 53.34 grams of the limiting one is going to be used up. Some of this 19 grams is going to be left over because we have excess. So it says which reactant is limiting. Aluminum bromide. Oops, let me go up here. Aluminum bromide, right? Which reactant is in excess? Fluorine. Now, this is just like, remember we did the males, females problems, and we had females left over, right? Originally, when I introduced this. Way back, it is the same. I just want to point it out. We're not. Because we had 18 females, and we needed 12. We had 6 excess females from the previous page, right? 6 excess left over. It's the same thing in this problem. We have 0.5 moles, we only need 0.3. That means there is 0.2000 mole excess fluorine. So we'll go down here, we have 0.2000 mole of fluorine in excess. Now, how many grams of the reactant excess are left over? Well, let's just take the moles and convert it to grams, right? So 0.2000 moles of fluorine. 1 mole of fluorine is 38 grams. So how many grams left over? 7.6000, right? Grams of fluorine. How many moles of each product produced? How many moles of each product produced? So we're going to go up top here. These two for moles. We're going to draw an arrow over. And that arrow is going to start with what we have of the limiting reactant, right? Because when the limiting reactant runs out, you're done making product, correct? So you always, you have to come off of what you have of the limiting. And what we have of the limiting is this box. It's either going to be this box if it's limiting, or if this reactant's limiting, it would be this box, right? You always come off of what you have of the limiting. So it doesn't have to look pretty. I'm going to come off of what I have of the limiting. I'm going to draw an arrow right here. And my mole factor fraction is, for this one, 2/2. So I'm going to produce 0.2000 moles of that. And my mole factor fraction here for the bromine is 3/2. So if I take my 0.2 times 3 is 0.6 again, you have it. I'm going to produce 0.3 moles of bromine. So let's fill this in down here. My moles of aluminum bromide down here is 0.2000 aluminum fluoride and 0.3000 mole of bromine. And then the next question says, the next two is how many grams of each product produced. So now we're going to calculate, finally, we're going to calculate the grams here. And we're going to calculate the grams here. Right? We don't know how many grams. Well, we've got the moles. All we got to do is convert these moles to grams, right? So down here, let's do that. Only 3 moles here. Only 3 moles of bromine. One mole of bromine. How many grams? Check your periodic table. Multiply 1 bromine times 2. How many grams? 159.81 or 80? Is it 81? 81? 81?
I got 0.
80? 80. You got 80. So 159.80 grams of bromine. Okay, this says 5 sig figs, it says 4. So if we do 4 sig figs in our answer, we get 47.94, is that right? 47.94 grams here? All right, so 40. And then how many grams of aluminum fluoride are produced? Point 2 mole of aluminum fluoride. One mole of aluminum fluoride. How many grams? 83.98. Yeah. The moles cancel out. Moles cancel out. And 16.80. Now, you're going to be impressed. We're making refrigerator art here, by the way. Just put this on your, you should just put this page on your refrigerator. Just let people comment on it, because we're not done yet. Now watch this. You're going to be impressed that everything is going to work out. I'm going to draw a fancy arrow. See if you can draw your fancy arrow the same as me. Maybe your arrow is going to be better than mine, but I'm going to bring this down like this. And I'm going to point it right here. This is going to be a beautiful looking arrow. There we go. Look at that arrow. What is your mass of total products? What is your mass of total products? My total product mass is, I'm going to put an equal sign here. My total product mass, 64.74 grams, right? If we add those together, so 64.74 grams. Total product produced, right? Now, if the law of conservation of matter holds, which it does, that should equal, so does it equal the total grams of reactants that reacted? That sounds complicated, but it's not. Does that equal the total grams of both reactants that reacted? I couldn't say that 3 times fast. Okay. We know that 64.74 grams here was produced by the limiting one, right? How many grams of limiting? 53.34. This is gone, correct? So let's figure it out here. We know that how much aluminum bromide reacted here was this was our limiting, right? 53.34 grams reacted at that. That goes into the 64.74 for sure. It's gone on, if it's gone on the reactant side, it's produced as a product, and this is the total product. Plus, let's do this. Now, of the excess is fluorine. How many grams of fluorine did we start with? 19, right? We started with 19. How many grams did we have in excess? We calculated the excess grams in letter G. We had 7.600 left over, correct? That means how many grams reacted out of the 19 that you had, because we had 7.6 left over. If we just subtract this, then we know that 11.40 grams reacted. What do we get when we add these two up? 64.74 grams, right? Which is what it should. How many grams of reactants reacted? 53.34 grams of aluminum, that is gone. Out of the 19 grams of fluorine, which is in excess, 11.4 grams reacted, 7.6 were left over. It matches how much product grams I should produce. Woo. We've come a long way, right? We've written formulas of compounds. Also, if we go up here, we've studied reactants or reactions. This right here is a single replacement reaction. Fluorine replaces bromine, by the way. So we've written formulas like aluminum bromide. We've looked at reactions, identified types of reactions. We've converted grams to moles, moles to grams. And now we put all of that into our reactions to calculate how many grams and so on. So we've come a long way, Now on the next page, I will set this up for you. And maybe I'll put the answers up. I'm not going to go through this one completely, but I'll set it up for you. You should be able to get the same thing to happen if you calculate this out. So it wants to, we're going to calculate how much we have here, how much we need here, how much we have here, and this one actually goes the other way, how much we need here. So this is A, B, C, and it actually calculates this as D, going back this way. And then it's going to have you calculate how many moles of each product here. Try this out a little bit. Monday we'll put some of this up there. But try this out a little bit. It should work out the same way. All right, let's go to the next page, percent yield. And then we can go back and finish where we started today with our quiz question. So what is the percent yield of a reaction that produces 12.5 grams of Freon, CF2Cl2, from 32.9 grams of CCl4 and excess HF? So just like we did our quiz questions, and you have a lab coming up where you'll calculate percent yield. So this is the actual yield or experimental yield. Actual, experimental, lab yield, whatever. Probably we would call it experimental yield. So we just need to calculate what we've done before. Hopefully this problem can go pretty smooth. We're gonna calculate moles. Then we're going moles to moles here to figure out what is our theoretical yield. So our theoretical yield is when we run it through the equation, assuming that's nothing's lost and everything works out perfect. But in a lab, things are going to stick to beakers, stirring rods, all kinds of stuff. There could be side reactions. So 32.9 grams. CCl4, how many grams in a mole of CCl4? How many grams per mole CCl4?
Fifty-three point eight one.
153.81, 153.81, 153.81 vertical knots. Okay, 153.81. So my starting moles here is 0.2139. How many moles of CF2Cl2 am I going to produce? What is my mole ratio fraction? I'm boring 1/1. Ugh. 0.2139. And then we're just going to convert this 0.2139 moles to grams, right? We always keep moles underneath here. So I'm going to put 1 mole of CF2Cl2 is how many grams of CF2Cl2? How many grams do we get there then? How many grams per mole here? CF2Cl2. Somebody yell it out. 120.91. Yes?
Yep.
So 120.91. So if we multiply that by our whatever we have left in our calculator, it's probably still in our calculator, we would get a theoretical yield of 25.86 grams, right? All right, so now we need a percent yield. And you probably can figure out what it is, but I'll put it up here. Percent yield is going to be actual in the numerator, or experimental, or lab results, divided by theoretical, and then multiply that by 100, add your percent sign on there, huh? So we should get 12.5 then. So my percent yield is going to be 12.5 grams divided by 25.86 grams. I'm going to multiply by 100. And I'm going to add the percent sign. If I do that, I am going to get 48.3%. So why don't we go back then and finish our quiz question that we started? So for our quiz question that we started in the beginning, we do actual divided by theoretical. 50 grams divided by 60.8 grams. We did that. Right, yeah. Okay. That should get you through all part one. Now, I do not do these combustion problems here, or these analysis, determining the formula of hydrogen by combustion. I do not do them the way the book does them, or perhaps, I don't think I'll explain it all. I do it strictly the way we've done it before by empirical formula. I come back to what we did before. So we will start out there next time and do those. So this should get you through our part one. Right? This should get you through our part one. You do not, the quiz questions were still only at 1 through 11. So we haven't had 1 through 11 on the quiz, and then 12 through 25 would be all part two. Have a good rest of your day.